So the first skill that we learned from chapter 17 was thinking about equilibrium, thinking about equilibrium constants, reaction quotients, and interconverting pressure-based and concentration-based equilibrium constants. The next section in the last two sample problems focused on a comparison of Q versus K to think about looking at a snapshot of where your reaction is at, which is Q, versus where you want to be, which is K, to determine which way the reaction is going to shift. The next section and the next big skill that's important to think about is actually solving equilibrium problems. And this is really important in a practical sense because when you do a chemical reaction, you're going to want to be able to look at and think about, where you want to end up. How much product are you going to make? Are there things that you can do to shift that equilibrium to favor the production of the material that you're interested in? So, as we kind of talked about in lecture 19 when you had kind of this set of sheets that was given out, there's basically two kinds of equilibrium problems. The first type, which are kind of less common, is you're given some equilibrium quantities of materials and you're going to solve for the equilibrium constant. We'll do a couple problems that deal with that, but most of the problems are going to be kind of this type 2 problem. You're going to be given an equilibrium constant for a reaction, and the question is just going to ask you, when you reach equilibrium, how much stuff do you have? So the first kind of problem, though, deals with determining the equilibrium constant. So I'm going to work through, again, the in-class problem that we had to kind of stress this in terms of what we call a relatively easy problem. So in this case, we're looking at the reaction of H2 and I2 gas to give us 2 molecules of HI. They tell us at equilibrium, we have a 1.5 liter flask containing this many quantities of these 3 species. So we're going to work through as we can consider equilibrium problems using a very systematic method for solving these problems. And generally I like to do this because when I give partial credit on exams and quizzes for these problems, you will get partial credit as you work through each of these steps. So the first thing you always want to do is write a balanced chemical equation. In this case, the equation was provided for us and it's already balanced, so we don't need to do anything further. The second step is to write the reaction quotient, and in this case, this should be a C here. In this case, we're going to write QC because values are given in terms of moles in a certain volume. So QP is equal to, and again, we get our reaction quotient from our chemical equation, the concentration of products raised to powers that are coefficients over the product of the reactants. So that's our reaction quotient for this problem here. First step, write a balanced chemical equation. Second step, write the reaction quotient. Third step, and these are what we call preliminary steps, these first 3 steps, are making sure that everything has the correct units. If we're talking about Kp or Kc values, again, this should be Kc, we're going to have Kc be units of molarity, Kp will be units of atmosphere. So in this case, we need to figure out the concentration of each species. So they tell us that the equilibrium concentration of H2 is 1.8 moles of H2 in 1.50 liters, and that's 1.20 molar. The concentration of I2 at equilibrium is equal to 0.520 moles of HI in 1.50 liters, and that's 0.347 molar. And then the concentration of I2 at equilibrium is 1.80 moles I2, 1.50 liters, and that's also 1.20 molar. So this problem asks us to determine K. So Kc and QC are related in that they have the same species and the same overall form, but this is a concentration of where you're at. This is the concentration at equilibrium. So that's why I'm writing these little EQs here to remind myself that Kc is the same kind of format as QC, except the concentrations that need to go in for Kc are equilibrium values. Well, since these were equilibrium values that were given us at equilibrium, we can just plug these values right in. 0.347, and that's going to be squared, over 1.20 and 1.20. 8.36 times 10 to the minus second. And again, notice there are no units with equilibrium constants. So pretty straightforward problem to determine K. You determine K by using equilibrium concentrations of your species.